Today's is going to be a fairly short video since it's Friday. And on Fridays, we just don't get that much done in class since it's only a 28-minute class, plus there'll be grading to do. So I'm not expecting to get a whole lot done. I'm just going to cover this with you. I don't think that there's going to be homework over the weekend. There really doesn't need to be homework over the weekend. We actually should be able to finish up this chapter, if not by the end of the semester, shortly thereafter. So we're moving at a pretty good pace here. Excuse me. I want to start talking now about centripetal acceleration. Let's review a little bit. We've talked about some of the factors already involved in motion. We've talked about distance, which in a circular environment is actually going to be angular position and arc length. We talked about changing those positions in linear kinematics. That would be velocity or speed. In circular kinematics, that's going to be tangential speed, which is the rate of changing my arc length, or I'm talking about angular velocity, which is the rate of changing my angular position. Now we're going to talk about acceleration. That's actually the last piece of kinematics that we had in Chapter 3, acceleration. But you look at the title of this chapter. The title of the chapter is circular motion with constant speed. How is it possible to have constant speed and yet experience acceleration? If I'm moving at a constant speed in a circular path, excuse me, how can I also have acceleration? I want you to pause the video, actually stop it, and think about this. I want to see if you can come up with the idea of where can I get acceleration with constant speed? Pause it. Okay, hopefully you were able to come up with some ideas with this. The key here is that we're talking about constant speed. But the definition of acceleration, by definition, it is the change in velocity all over the change in time, or the rate of changing velocity. Changing velocity means I have to change any piece of velocity. Velocity is a vector. Because it's a vector, it's made up of speed and direction. If I change either of those two, I will be changing velocity. When I travel around a circle, I am constantly changing velocity. Constantly changing velocity. Every time my object moves, it wants to go straight. It wants to go straight, but it can't. So it is being pulled into the circle. Now, I used to use a description by subtracting vectors using the moon. I don't do that anymore. I don't like it, and I'm not even sure that it is mathematically an accurate way of looking at it. So I'm dumping that. I haven't gone in and changed the notes yet for it. So we'll just cross it out. Don't need to worry about it. But I do want you to notice that it is accelerating because it is changing direction. It would be a great question for me to ask you in the future. How is it possible to experience constant speed around a circle and yet be accelerating? Well, how is it possible? Because you are constantly changing direction. And when you change direction, that means you are changing your velocity. Changing your velocity, and changing your velocity absolutely means you are accelerating. It doesn't have to be change in speed. It can be change in direction. I want you to think about this from the back door instead. Why is it things want to keep staying in motion in the same direction? It's their inertia. First law of motion. Objects in motion want to stay in motion with the same speed and in the same direction. Unless, what's the only thing that's going to change that according to Newton's first law? If it's acted on by an unbalanced force. So to keep pulling it in this way, it wants to keep going out, but what pulls it in has to be an unbalanced force. It's the only thing that disrupts its inertia. All right, so you know that there's got to be an unbalanced force acting on this. If I am applying an unbalanced force according to Newton's second law, what am I going to get as a result? Newton's second law says an unbalanced force acting on an object causes the object to accelerate. So as soon as an unbalanced force came into the picture, it had to be acceleration. And there has to be an unbalanced force in order to get it to change directions. So whether you look at it as changing directions is how I change my velocity, which is the definition of acceleration, or if I look at it from the fact that the only way I can change directions is by applying an unbalanced force, and Newton's second law says that the result of that will always be acceleration. Either way, I've got acceleration going on here. So that is an important piece to this. And I'm just, instead of proving this with that circle, I'm just going to say, notice that the acceleration, the force is pulling it in, therefore the acceleration is in. Notice that since the force, and we'll talk about the force later on in this chapter, notice that since the force is pulling the object in toward the center, let's see, what was Newton's second law? An unbalanced force acting on an object causes the object to accelerate in the direction of the force. If it's pulling the object in towards the center, then the acceleration is pointed to the center. Is pointed or directed toward the center of the circle. Okay, and for letter C, again, I was using the moon for that. I've said all I need to say. Acceleration is pointed toward the center. And I'm just going to give you some formulas. I'm not as in love with this derivation as I am the one before, but we'll work through it anyway. This is going to be a given. This formula is standard and given and proven, and I'm not going to go into how this happens. It just is. V squared over R. So we're just going to call this my given. Now I want to derive from that how I can find the centripetal acceleration, which by the way, that's kind of important. It's called centripetal because it's toward the center. Let's write that in here. Because it's pointed toward the center. Okay, so what I want to do in this derivation is get from centripetal acceleration that uses tangential speed to centripetal acceleration that uses angular velocity. So let's start with my given. I have a sub c is equal to v squared over r, and we're just going to say that that's given. And I already know how to go back and forth between v and omega. V is equal to r omega, and that was previously derived. We already proved the existence of that one in our last derivation, so we don't have to go through it again. Just look at the last derivation. All right, now I know that v is equal to r omega, so in place of v, I'm just going to put r omega. A sub c is equal to r omega, but notice that v is squared. So it's going to have to be r omega squared all over r. Oh, wow, you see where this is going. Substitution. Now I'm just going to distribute my square throughout the whole thing. So a sub c is equal to r squared times omega squared all over r. And that's just the distributive property. And finally, I'm going to just shorten this up, tighten it up. I can get rid of this r by getting rid of one of these r's. So my last one is going to be a sub c is equal to r omega squared. And that is just cancellation. And I think I'm going to hold off. I'm not going to give you folks homework over the weekend. Um, I actually think I am going to. I'm sorry. Let's look. I am sorry. I know that it was nice, the thought of maybe not having homework, but I'd love to be able to get this chapter done, and this is not going to be a long video anyway, so hopefully you'll have more time to be able to work on this. Let's look at 6.4. 6.4 is calculate the centripetal acceleration of a car traveling on a circular racetrack of radius 1,000 meters at a speed of 180 kilometers per hour. So I already have a speed and I have my radius. I'm going to write down everything I know. I know that r is equal to 1,000 meters. And I know that my tangential speed, it has to be tangential because it's going around a track, and I know that it's tangential speed and not angular velocity because it gives it to me in kilometers per hour. That is a unit of tangential speed. Meters per second, feet per second, kilometers per hour. As long as it's a distance over time, it's tangential speed. So v is equal to 180 kilometers per hour, and I need to find the centripetal acceleration. A sub c is equal to, I don't know, we're going to work that one through. My kilometers per hour, I have to convert my kilometers anyway, so let's convert kilometers per hour to meters per second. It's just one shot at it, so we might as well do it all at once. So I've got 180 kilometers per hour is what I'm given, and my ratio is 0.278 meters per second is the same as 1 kilometer per hour. You have that on your conversion sheet. So once I do that, I find that my tangential speed is actually 50 meters per second. And now I have it in meters and my radius is in meters. That's why I had to do that. And since I was converting it anyway, I don't want it in meters per hour. That would be kind of stupid. So it was easier, in fact, to convert it to meters per second than it would have been to have to convert two pieces. No, actually, I said that wrong. I apologize. It's just as easy to convert kilometers per hour to meters per second as just converting kilometers to meters. So now I need to find a sub c when I'm given this. I have a formula that works for that. This is the formula. And I'm going to go ahead and put that in. A sub c is equal to 50 squared all over 1,000. Do the math on it and you end up with 2.5 meters per second squared. Now let's work through the units for this. For my v, I have meters per second, and that's going to be squared all over meters. So I end up having meters per second times meters per second all over meters. Work that out, and I'm going to put it up here. So I have meters squared all over second squared divided by meters, which is the same as times 1 over meter. This cancels out with that, and I'm left with meters per second squared. So my units work out perfectly with that. And of course, we always want to be attentive to that, making sure that we're getting the right units for the problem we have. The next one, 6.5, is a red blood cell suspended in a liquid in a tube rotates in an ultracentrifuge in a circular path of radius 0.1 meters. The tube makes 800 revolutions per second. Calculate the centripetal acceleration of the cell. So I'm going to write down what I know. I know that my radius is 0.1 meters. I know that it makes a circular path, or it makes 800 revolutions per second. So is that theta? Is that S? Is that V? Is that omega? Let's look at it. Boy, am I happy about this. I got to tell you. It is 800 revolutions. Okay, that's theta. Revolutions is a theta marking. Per seconds is time. Theta over t, we're talking about omega here. We're talking about angular velocity. So my angular velocity is equal to 800 revolutions per second. And I'm looking for the centripetal acceleration of the cell. A sub c is equal to, I don't know. Now I have a formula that will work for that. It was the formula that we just derived. A sub c is equal to r omega squared. There's a little problem with that though. Let's look at this. At the heart of this is v is equal to r omega. V is equal to r omega came from theta is equal to s over r. This requires radians because it's a definition. And if this has to have radians, remember that we said it's required to use radians for this because the foundation of that equation is theta is equal to s over r. Well, the foundation of this equation is v is equal to r omega, and that depends on theta is equal to s over r. The whole thing requires radians. I have to be in radians. Let me say that again. To use v is equal to r omega, gotta have radians. To use a sub c is equal to r omega squared, gotta have radians. To use theta is equal to s over r, gotta have radians. Do you get the feeling that really when you're using these formulas, just use radians because you can't go wrong if it's in radians. So we're going to have to convert our 800 revolutions per second to radians per second. That's pretty straightforward. 800 revolutions per second, and I don't need to worry about the seconds. That's going to just stay there, and I know that one revolution is 2 pi radians, so I just have to multiply the 800 by 2 pi, and it ends up being 5,024 radians per second. All right, now that I know my radians per second for omega, I can find a sub c. A sub c is equal to r omega squared. R is 0.1. Remember that it is just the omega that is squared. There's no parentheses around it. It's just the omega. So it's going to be times 5,024 squared. I'm expecting it to be a little big. 2.5 times 10 to the 6th meters per second squared. Again, let's talk about the units here. So I have meters here, and I have radians per second squared. So what I really have is meters times radians squared all over seconds squared. Oh wait, radians is not a unit, so I'm left with meters per second squared. That's how that's allowed to be the case. All right, your homework for tonight is going to be, and over the weekend, is going to be 16 through 20 and 22. 16 through 20, 22. I think they're pretty straightforward. Just remember that for G's, and it talks about G's in number 18, remember that a G is 9.81 meters per second squared. So if I have 150,000 of these, it's 150,000 times this. And yeah, that one's pretty straightforward. All of these are fairly straightforward. You don't need to be dealing with things that are terribly difficult. I actually am going to dump number 22. I'm going to take that one off the table for you. So it's just 16 through 20. Not a whole lot. You got 5 problems. 5 problems you can work through that without a lot of difficulty. Let me know if you run into any trouble with this, but the formulas then, I'm going to write them off to the side. Make sure that you keep having them in front of you, and then we'll be done with this. So you've got theta is equal to s over r. Remember, you have to have radians for that. You have v is equal to delta s all over delta t. Omega is equal to delta theta all over delta t. I should be using the names for this. Tangential speed is the change in the arc length over time. Angular velocity is the change in the angular position all over time. I also have v is equal to r omega. If I have this one, I have to have radians. I also know that a sub c is equal to v squared over r. And I know that a sub c is equal to r omega squared. Oh, and guess what? You have to have radians for that one too. So pretty much, except for this equation, when you see an omega, it should be in radians. And of course, theta is equal to s over r. Has to be in radians. All right, folks, let me know if you have any trouble with this. These are kind of fun problems, I think, because they're straightforward as long as you know your terms. All right, have a good weekend.